Look at this spiral galaxy surrounded by countless stars. Its arms of stars, gas, and dust curve gracefully around the center. Let's take a closer look. But this spiral pattern is not exclusive to galaxies. Similar forms can also appear in tropical cyclones. Here, massive cloud bands rotate around a remarkably calm eye as the storm moves northwestward. And most of us have probably seen a seashell like this. A galaxy, a typhoon, and a seashell may seem completely unrelated, but they share something striking. Can you see it? The spiral, a curve that grows without losing its shape. Let's enter the world of the logarithmic spiral. To understand this curve, let's begin with the simple growth rule. As the angle changes, suppose the radius grows at a rate proportional to its current size. dr over d theta is equal to br. Here, r is the radius, theta is the angle, and b controls how tightly the spiral winds. Solving this equation gives r is equal to a times e to the b theta. This is the equation of a logarithmic spiral. Now, increase the angle by the same amount, delta theta, again and again. Each time, the radius is multiplied by the same factor. So, the radius forms a geometric sequence. The curve does not grow by adding the same distance. It grows by multiplying its size by the same ratio. Taking the logarithm of both sides gives the logarithm of r is equal to the logarithm of a plus b theta. So the logarithm of the radius changes linearly with the angle. This linear relationship between the logarithm of r and theta is where the name logarithmic spiral comes from. Now comes its most remarkable property. Rotate the spiral by any angle phi. Its radius changes by a corresponding scale factor. By compensating for that change, the rotated curve overlaps perfectly with the original. In other words, every enlarged part of the spiral is another copy of the whole. Even as it grows larger and larger, it never truly changes its shape. This property is called self-similarity. Another remarkable property of the logarithmic spiral is its constant angle. At any point, draw the radius from the center to the curve and draw the tangent to the curve. The angle between them always remains the same. For a logarithmic spiral, this angle satisfies tangent alpha is 1 over b. As we move along the spiral, the radius and tangent both rotate, but their angle never changes. This is why it is called an equiangular spiral. The parameter b determines how tightly the curve winds. A smaller b produces a tighter spiral, while a larger b produces a wider, more open one. The angle may differ from one spiral to another, but along each spiral it remains constant. A smooth curve can hide another curve within it. This hidden curve is called its evolute. At every point on the curve, imagine drawing the circle that best matches its local bending. As we trace the centers of these circles, they form another curve, the evolute. For an ellipse, the result is a completely different shape, a beautiful curve with 4 sharp cusps. But the logarithmic spiral does something remarkable. Its evolute is another logarithmic spiral. After the proper rotation and scaling, the evolute overlaps perfectly with the original curve. Even its hidden curve preserves the same shape. This is yet another consequence of self-similarity. The mathematician Jacob Bernoulli was deeply fascinated by this self-similar curve. He called it Spira Mirabilis, the marvelous spiral. He even asked for a logarithmic spiral to be engraved on his tombstone. But contrary to his wish, the sculptor carved the wrong kind of spiral. Even Bernoulli's final spiral failed to resemble itself. Here is the logarithmic spiral. Now let's use it to build a three-dimensional shell. From the top view, we follow the spiral path outward, and the radius keeps increasing. But a shell is not just a flat curve. So let's switch it to the side view and give it an elliptical cross-section. As the spiral rotates and expands, this cross-section grows as well. Sweeping that growing cross-section along the path creates a shell-like form. This gives us a simple geometric picture of how a seashell can grow. Instead of rebuilding the entire shell, it keeps adding new material at its opening. As long as the same growth rule is repeated, the overall form can remain similar. A seashell grows by adding new material at its opening, allowing it to become larger while preserving its overall form. A tropical cyclone is fueled by warm, moist air and organized convection, while the Coriolis effect helps produce its rotation. Together, these processes organize this cloud into sweeping spiral bands, and galactic spiral arms can emerge from large-scale gravitational dynamics, creating patterns of higher density in stars, gas, and dust. These structures arise through entirely different mechanisms, yet remarkably, their geometry can look strikingly similar. In nature, none of them forms a perfect logarithmic spiral, but each can echo its characteristic shape. When the angle increases by equal amount, the radius of a logarithmic spiral grows by the same ratio. Rotate it, enlarge it, and its shape remains unchanged. Different natural processes can create remarkably similar geometry. From seashells and tropical cyclones to entire galaxies. A simple rule of growth can echo from a shell to a storm and even across a galaxy. The logarithmic spiral is only one member of a much larger family. Next time, we may meet a spiral that approaches the center forever, the hyperbolic spiral. Please subscribe, and I'll see you there.